Deep learning for physical layer 5G wireless techniques, opportunities, challenges, and solutions. Abstract. The new demands for high reliability and ultra high capacity wireless communication has led to extensive research into 5G communications. However, current communication systems, which were designed on the basis of conventional communication theories, significantly restrict further performance improvements and lead to self limitations. Recently, the emerging deep learning techniques have been recognized as a promising tool for handling the complicated communication systems, and their potential for optimizing wireless communications has been demonstrated. Introduction. The explosive growth of incremental data, high speed, and low latency communication scenarios has brought significant challenges to the current communication approaches, and the increased complexity of network structures and computation degrades the performance of conventional communication systems. Recently, to improve the performance of fifth generation 5G communications, non non-orthogonal multiple access NOMA, massive multiple input multiple output MIMO, multimeter wave wave technologies, and other appealing techniques have been developed. However, as reported by IBM, the explosive data will be over 40 trillion Gbits in 2020 and a 44-fold increase from 2009, and it is projected that the amount of connected equipment will gallon to 56 billion. Notably, since the existing communication method have fundamental limitations in delivering the system structure information and handling large quantities of data, new communication theories should be established to meet the requirement of 5G systems. Deep learning based NOMA. NOMA is a 5G technique due to its potential from boosting spectral efficiency and system capacity. However, user mobility leads to highly complex channel conditions in each link. The performance of NOMA based frameworks depends on the CSI because interference cancellations requires accurate knowledge of the very complex channel conditions. We incorporate deep learning into the NOMA framework and corroborate its superior performance. Input to the specific channels and output symbols, input symbol and output symbol. The process is encoding and decoding, structure iterative support detection, DNN with softmax functions, DNN with linear functions into SIC, deep learning based NOMA system for data detection, encoding and decoding, deep learning based massive MIMO. As perfect CSI has great effect on potential gains of massive MIMO, it would make sense to investigate high accurate channel estimation issues for acquiring perfect CSI. We consider frameworks that adopt deep learning techniques into massive MIMO systems for direction of arrivals DOA and channel estimation by fully utilizing the spatial information. Furthermore, it is worth pointing out that the DNN is a good candidate to conduct accurate CSI reconstruction for super performance channel estimate of massive MIMO. Although massive MIMO is a possible strategy for further communication networks to maximize spectrum efficiency, a very large spatial complexity of the system reduces its performance. Concentrating on the direction of arrival DOA, estimation and channel estimation issues, we apply deep learning to a massive MIMO system, and the feasibility of this novel framework is verified using extensive simulations. Deep learning based MM-Wave. MM-Wave communication has a 10-fold increase in bandwidth compared with the current wireless networks, but MM-Wave based scenarios lead to ultra high power consumption and limited link gain in correlated channels. Here we employ deep learning in a MM-Wave massive MIMO system and show its excellent performance in terms of hybrid precoding. The MM-wave technique has been given great importance by the research community since it is an alternative approach for improving spectrum efficiency and facilitating the design of large-scale communication networks. However, there are many challenges in the context of MM-wave technique, such as path loss, penetration loss, and the high power consumption. In particular, hybrid precoding has been developed to limit the power consumption and the hardware cost of MM wave based systems, but the existing hybrid precoding method requires bit allocation and have a high computational complexity. We envision that deep learning can optimize the hybrid precoding in MM wave system following its remarkable performance when applied to the NOMA and massive MIMO. Hence, we integrate deep learning into mmWave, massive MIMO, and purpose a high efficiency hybrid precoding scheme. Overview of deep learning for wireless communications. In general, DNN has become one of the most universal generative models. As stated by the popular universal approximation theorem, by employing the multi-layer perceptron MLP mean a feed forward neutral network with a single hidden layer is capable of approximating continuous functions on compact subsets of Rn, where Rn represents the fields of real numbers with n dimensions. The performance of the MIMO detection is related to the choice of loss function, and the developed NN stimulation resulting verify that is achieved superior performance in terms of the bit error ratio BER as compared with the several existing works, including the zero forcing, approximate message passing, and semi-definition reflexive approaches. Future challenges and opportunities. The remarkable capacities of the deep learning techniques to deal with the enormous amount of data and sharply changing environment indicates that it can improve the performance of NOMA, massive MIMO, and the MM-wave network. However, many issues have not been resolved, and there are some factors that can overwhelm the system performance. There are numerous challenges to overcome and several new techniques to explore in the future. Model compression for deep learning system based 5G. One limitation lies in current deep learning based framework is that some deep learning models for addressing communication issue required high computational complexity, which hinders its implementation on small terminals such as mobile phones. Till now, a large branch of such frameworks are designed based on the LSTM and the CNN conclusion. In this article, inspired by the state-of-art deep learning and 5G communications, we summarize the recent development of deep learning-based wireless physical layers and describe several novel and efficient deep learning-based 5G communication frameworks. In particular, focusing on 5G, these frameworks based on the deep learning are presented and the performance are investigated, which are NOMA, massive MIMO, and MM-wave hybrid precoding. However, it must be admitted that many technical implementations are there infancy with open research questions, and it is a long roadway ahead to use the deep learning concept to address wireless physical layer issue thoroughly. Thank you.